Hello, today I've got an interesting video on a previous project that I never took to life essentially, and we're going to go over brief schematics and what this device does and how it's supposed to work and everything. And I think there's a lot of learning here, so let's get into it. So the device overall was supposed to be a tracker of some sort. It was a multi-sensor board. It had 5G connectivity to it. It had Bluetooth. It had UHF. It was a very purposely built over-the-top tracking device. And it had all these interesting sensors onto it. So what entirely was it? It was meant for tracking, as I said, and we're going to go over the few functionalities it has. So in the overview page here, as I told you, I like to do this now, is how the whole system operates. So we got our power, our MCU, that of our choice. We've separated into the RF, UHF module, SAR module, our Bluetooth module, and sensor modules. I also like to put the mounting holes in this page because I do not think they fit anywhere else. And here we are in the power section. We see we have a USB-C battery charger / system. It's always good to label what you're doing, what this circuit does. As you can see, I've put notes all over the place. And this is something that I highly encourage doing to get a feel for, just to get a feel and get into the habit of writing notes down. Because when you come back to this in the future, you may not know what you're actually reading or what this actual circuit does. So begin with USB-C input, standard USB-C. We put down our pull down resistors for what we need. I've read somewhere in the specification that it may require pull-up and data lines, but they're currently as do not fit. So I put these, I've never had to, but I'm unsure about this now, and I've put them in there because I can always fit them if I need to. They're 0603 packaged. And packaging is one of the main things you need to keep in mind of, is that if you are tending to play around with this device and you expect some changes to be made, make the package size as comfortable with what you are to soldering. So for me it's 0603, and I get a bit finicky with the 0402s, and I just wouldn't touch anything lower than that. Here we are coming in. So TVS diode, always include these when you have any ports to the outside world. Ferrite bead, it's just acting as a pi filter really, and I believe I had this cutoff at 132 kilohertz. Of course, this is arbitrary if you're not too sure, but it's always good to have one in, and this one you can experiment with and decide what values, but as long as you've got it in there, you can experiment with. I've got into this very overkill and over the top piece of load sharing battery charge IC. And I say it's over the top because for this type of system, had it gone into a testing phase and whatnot, it doesn't really need this IC because it's only ever going to be used in the field, and if it's a tracker, it's going to be placed somewhere else, and no one will ever charge it or whatever. It just really needs to be charged and go. So why have I done this? And I said I think this IC is really quite nifty, and this is really the best way if you have a rechargeable circuit of some sort to have this load sharing. I see where some portion gets delivered out to your system and other portion gets delivered to your battery charger. It smartly diverts the power for which way it needs to go. I've took this from the actual data sheet of this typical description, and I've put in some values. I always recommend putting in some values here. This N/N2 setting tables. So for why have I decided to put these in? Again, I've placed 0 ohm resistors because I am unsure of what it's going in. So I've got N2 is to 1, N1 is 0, so this is set by external resistor ILM to VSS. So this external resistor is one of the pins here, I believe. So it's the I set pin. And this is the set for how much current we will allow in for fast charge. And for here, I think it's 1.5 amps for USB-C. So we are setting this here to kind of match it, if not a bit more, for how much we want. We always have to keep in mind of our inputs also. It's got inbuilt, you can put some LEDs on there, and this is something I forgot multiple times in project, is having like a power good LED. Very useful piece of thing to have a visual indication to see whether your system works or not. So besides that, not much to it. There are multiple ways to do this kind of configuration. For example, if it was really simple, I would have just chucked in a FET in and have it filled like a P-channel FET. And should the USB be present, it'll turn the gate on, and they'll stop conducting throughout the P-channel FET, turning it on. So moving on, we have to this buck boost converter here, and as you can see, there is a slight issue with this, but I will get to it. It's the same one I've used in multiple projects before. I've put the pi filter in front of the output capacitor here. Now you may think, well, this shouldn't really be a problem because your feedback is connected to the V out, and this will pose a problem. And I'm gonna tell you guys this, as I say this multiple times, that when the datasheet says so, that you follow something, you have to follow it to the absolute T, to the absolute core. So if it says place these specific output capacitors, so these 22 microfarad capacitors, you place them in and have your rest circuitry on afterwards. Because what this essentially has done here is taking output with reference to this inductor over here, and it's causing some stability issues. It's not really getting a positive feedback from it. It's not getting the feedback it expects. So I was getting 0.9 volts in this configuration here when I was testing it. It was not until I would see and say this was the only difference. I've removed this inductor, shorted this across, and because it's only nanofarads, it's not really going to make a big difference. And it was working again. So always keep the layout and if you're putting a filter of some sort, place it after the output capacitors. Get another power good LED just for good keeping. See if it's all working. Some calculations and some highlights for anything that I may find an issue. So this part I was unsure of, so I've included the data sheet here. Battery protection for our battery. It could do with a reverse polarity diode or some other reverse protection, as I do not think this comes with it. So that's to keep in mind of, and that will be added to the next iteration. Always need one if you're dealing with batteries. I've always put one. Never leave it out. Very important stuff. Feedback is to go into the micro to see how battery voltage is doing. Moving on to the schematic, we see it was quite a bit going on, but really it is quite simple. So we have it separated into the power section here of our microcontroller. You will notice with microcontrollers, sometimes you see them split into 3 parts, A, B, C, or whatever if it's a large device. And this is just for ease. This is just to easily read it. If you had your microcontroller all set up on one page, it can get quite clustered and complicated, and if you made a mistake and no one's checked it, or even if you're just checking yourself, you could easily get lost in it. Try and spread it out to make it easier to read. So again, I'm not really going to go through this too much because it's just generic stuff that you can find in the datasheet, so nothing special actually going on here. Also here, simple IOs going in and out. Nothing special going on here. These pins are highlighted red because I'm not using them anymore, so I'll need to remove them. Your crystal SD card, it was connected like this. This is through SPI, and I've had luck using it in this configuration. I can't even remember where I got it now, but luckily I found this and it's worked so far nicely. Harnesses, always keep in mind to put the location of where these things are so you don't end up scrolling through all the schematics. UART switch, so this was really just a simple switch between the Bluetooth and just a general serial output thing for debugging purposes. TVS diode here for this purpose, put a symbol there so people would know. And simple JTAG header. Everything else is just user interface, and I highly recommend adding 2 buttons and an RGB LED or an LED of some sort for debugging purposes, as it's always nice to get a visual indication. Everyone will benefit from this, and if you really do not want to, you can just remove the component afterwards. If you feel you really don't need it, afterwards your debugging process is done. Or when you come to make a new revision or a new spin of the board. RF stuff here. So it was actually a LoRa module, I think we chose. It was an STM32WL55. And this again was just took from the schematic application notes. I've spoke about this in previous videos and I've had comments and discussions with other engineers and whatnot. And you're not going to get the most ideal output of this device if you're just taking application notes. Everyone is different. You got to tweak it to your own parameters. And I do realize that. But again, if I'm just getting something to work, if I just want something easy to work, the application notes and the reference schematics are there to help you. And there was even a bunch of, I've put in the description, there was a bunch of notes saying what this circuit is, how do you even design it for yourself. And I've put this in here just as something to get me going and started. So do not criticize anyone or chastise for not using them or saying it won't work, because it may not work as the best as it want, or the results that you may not completely match the results that, for example, ST have provided. But again, it gives you a good starting ground. So I won't go through any of this because it's inside the notes. I'll include in the description and such. But basically, it's a bunch of filters, and you can select whichever RF output you want between these RF switches and such, depending on the certain configurations that this chip had. UHF module is just a little standalone chip I got, communicating via SPI. Not much to it. It was quite interesting actually, because they had a few reference designs on what you could use it for, and they have a few reference designs on tagging systems and warehouse distribution systems where they use UHF for stock control and everything. So it was really interesting to read into it. But again, nothing else much. It's an interesting thing, so I won't go over this too much, but for certain placements, I think for this antenna here or C339338. I presume it's talking about this one, and I have to update this. But certain antennas have certain placements that you need to keep aware of for the component. So always do keep a note here, because when you do come to place the component or such, or the pad, or maybe you do have the pad embedded in the footprint of your antenna, you should just keep note of it to increase for reliability of how your antenna may or may not work. Sour module. So these sour modules come in a whole bunch of different flavors and configurations, but honestly it's been great. Like, the amount of documentation they provide to get these things up and running is fantastic. I highly recommend if you have a project related that needs something like that. A bit on the pricier end of things. I think these things were like £50 for a single thing, and honestly yeah, but it was really interesting to read into it and see a whole bunch of different configurations. Keep in mind that you do need a level shifter for this. I had made that mistake before not reading into it, but this speaks at 1.8 volts, so you need something to speak at 3v3 for your micro or whatever. So keep that in mind. Put in the schematic where you got it from. And the nice thing about this is I think they actually gave out a 1.8 volt output somewhere. I'm pretty sure there was. Can't find it now. But it was somewhere. One of these modules, they have a 1.8 volt output to give to your level shifter, so it was really quite good of them to do so. Again, nothing too much in here. All general schematic purposes. This one had GNSS and cellular, I think, so it was quite a comprehensive package. Actually, it was really interesting. A few different things: power control, network indicator, your antennas. If you're wondering about antenna placement and like choosing one, if you wanted to, they do give some recommendations for that, so I highly suggest you pick one out of them. There's a few listed there, so I think you'll find one for your needs. Again, a whole bunch of test points. I put test points everywhere as it really helps with the testing phase and whatnot, and everyone loves them. So Bluetooth module, this was simply because our chip did not have Bluetooth in them. In the chip, it was meant for LoRa, so we need an external Bluetooth module to do so. And I think this one's communicating off UART, and a lot of these empty pins I've just pulled down to ground to a known state. And again, nothing else too much going in here. I can't really speak on anything. I think arguably the most interesting part of this project was the amount of sensors on it, and yeah, let's get into it. Temperature and humidity here. I2C communications, nothing too special here. I've used this one in the past, it's decent. It gets the jobs easy setup. Motion, I think it was a bit overkill for this one, because we were selecting a motion sensor in the firmware engine. It was just like, let's go with this one. It was like, it's £6 for like a gesture sensing and like all you could do sensor, but we just needed to know if the product shook or what. It's really overkill for this, but it seemed really nifty, this sensor here, this LSM6DS V16XTR. Nifty, and I guess it's some learning, you know. It's always good to get some learning out of something. You always want to increase your knowledge and whatever, but if I had to really do this from if money was an object, and I would not choose this chip. I would pick something much more simpler, easier to configure, something that literally just says like accelerometer or whatever, and that's it. You know, it didn't need all these gesture sensing and whatever. Pressure sensor, again, I2C, nothing else too much, nothing else going on. Light sensor, this one I'm not too sure of, because I actually do need to get this checked out a bit. But this LDR portion, I think this is connected, so this is wrong a bit here. So you can see that because I'm on a 1mm grid, you can see all these issues pop up. So let's change that to 2.54. That should solve it. Yeah. So I had this issue with the grid with KiCad before, where I was using like a 0.1mm grid or something ridiculous like that. And you don't really need one for that purpose, believe it or not. You just need something that could move around, and it's not really that crucial in schematic creation. More crucial in PCB layout, but you know, once you've chose a grid size for all your components and whatever symbols, keep to that grid size. C2H4 sensor, so this is an ethylene sensor. It requires a potential static circuit, so this was a rough thing design. So what this potential static circuit does is, I think it took because it's a 4-terminal electrode, a 3-terminal electrode, it needs a bias reference voltage of some sort. So I think it was, if it's going into it, you have a reference voltage here. It's going out here, and this is connected through here, going down here. It's going to try and make the reference voltage as the same as these possible pins, and this is what you want to try and keep it the same. This is just a characteristics of the op amp, and what this purpose for here was to give a stable reference voltage for this pin. Coming into the sensing portion, this was literally just to output the larger signal coming in, so it's taken from the reference counter. The sensing force is just to output a larger signal, just generic amplification. Then put a potentiometer in there just to adjust it for what I wanted. You may be wondering what this FET here is for this transistor. And this was just something in the schematic that if you needed to switch off the system, it requires these 2 pins to be shorted so it couldn't be damaged essentially. So because this P channel right now it's on, it won't conduct through, though when it's off, so when there's no, and this will be pulled down to ground, this will be shorted throughout here, and that's essentially what will happen. So I'm unsure here because it's connected through, so I'll need to take a look into this to just make sure this is right over here. But again, loads of information on this type of circuit. I think it's commonly used within these types of electrochemical sensors and such, so it's quite an interesting read. Learn something new there with analog circuitry, so it was very interesting to see. CO2 sensor, nothing else, nothing too special, just I2C coming out of it. And the oxygen sensor, I think it was another electrochemical type thing, two electrode device. So this one it's a current output, and the easiest way to do that is to put resistors. It's the most simplest form of a current to voltage conversion, and you get the voltage drop across this, I believe, through the op amp. You amplify that signal and you get out the output. I have listed to have a gain of 100, but I would actually check this over. Again, this was just a brief first iteration. Never made it past this point in the design before I had to redo it all. So I thought rather than this go to waste, I would rather share it and you hope to learn something new out of it. Arbitrary cutoff frequency of 1 kilohertz. Again, I've put this here. I always put these low pass filters now in an analog signal, just because it is an analog signal and should have some form of filtering, and because it's there and I can mess around with the values and such. So that's all for this one. There is nothing really it was exciting for me to design this all and learn quite a few bits and things. But I hope you've learned and took something out of it, even though it seemed very brief and fast paced, but I didn't think there was much to it with all the reference circuitry that was used. But still, I hope this video was somewhat enjoyable. Hope you learned something new.